Alright, so I just wanted to make a quick video about this new idea of implicit differentiation. And so to start with, let's just define a function f of xy. And just think of this as an expression that involves an x and a y. So we might have like x cubed plus x squared minus 2xy. Okay, and now I want to plot where 2 is equal to f of xy. Oops. Good. And what you're seeing on the screen here is the result of this f of xy equals c. So the result of f of xy equals c, I just want to emphasize here, is a curve in the plane. Okay, and in particular you might notice that this is not a function, right? Because it does not pass a vertical line test. And so I wonder if we can differentiate such a thing. It is possible. This would be a very difficult thing if you set f of xy equals to 2 and tried to solve for y. That would be very difficult, right? Because you have this extra 2x times y there. You wouldn't be able to isolate the y. However, we don't need to do that. The idea behind implicit differentiation is that we're going to start off with f of xy equals c, and then we're going to just differentiate everything in place. And so before we do that, I just wanted to show you a few examples of what f of xy equals c might look like. So here's one example, and so we could try different points, and for example here at 2, maybe down here at down here. By the way, if you were to plot the inverse function, what would it be? So if we plot fg of xy, if we just reverse the x and y, right, if we make this x cubed plus y squared minus 2xy, right, and then we make this 2 equals g of xy, right, you see that this, you actually get the inverse function. Good. Some other functions that you might run into, so let's just try it. H of xy maybe equals, how about cosine of x plus sine of y. And down here we'll take h of xy equals 1 just for fun. I guess we can clear some of those. Good. So this is kind of a fun pattern. You can try different functions, right? So this isn't necessarily a single curve in the plane, right? It's lots of curves in the plane. But what I wanted to emphasize here is that you could still restrict the x and y, right, to a single circle or a single kind of diamond shape, and you could create a function out of that. You'd have to separate, you'd have to cut your function up into pieces, but it's possible to do that. It just takes a lot of work, and so we don't want to have to do that by hand. So we're going to just take a look to see how it is we can differentiate f of xy equals c, a curve of this form, and find the derivative without having to actually solve the system for y. Okay, so that's in the next video. So I would encourage you to play around with Desmos a little bit. Take a look at what f of xy equals c can actually give you. In all cases, it's going to be some kind of, if you can get pretty creative with your functions here. Maybe y cubed. Oops, that's not going to do very much. Y cubed plus maybe cosine x times y. Oop. I'm just making something up here. And then maybe 3 equals f of xy. Oh, it didn't like it that I redefined f of xy. I'll just delete this one. Okay. Oh, there it is. And so you can see something happen right here at the origin. But anyway, you can have fun with this. Again, the main point here is that this expression f of xy equals c gives you a curve in the plane. All right, that's it for now. Then the next video we're actually going to show how to differentiate these functions directly. I think if I can stop my recorder.